I know that's what y'all want to do. Where is Reagan today? Swimming. All right. So today we're doing logistic growth. And logistic growth, it's a BC topic only. It's literally like one specific type of question. So it looks like it's kind of a long note, but it's actually, I don't want to say relatively unimportant, but it's like such a small thing. And they're going to say like using logistic growth. So like they're going to tell you what it is. It's kind of the same with Oilers, right? Like it's a very specific thing. They're going to tell you you're doing it and that's it. Okay. So it says in exponential growth, we assume that the rate of increase or decrease of a population at any time t is directly proportional to the population. In other words, this is our like general like rate or proportional differential equation that we use. Okay. Remember, K is that constant of proportionality. However, in many situations, population growth levels off and approaches a limiting number that we're going to call L. So this is important. This is called the limiting number or carrying capacity. Okay, it's called carrying capacity because it's like what the environment can handle. Okay, and you guys, if you're in physics, you might have already talked about logistic growth a little bit. Okay, but maybe just not done the math of it. So think in your head, like, okay, the one that we always go to is like rabbit populations, right? Because they blow up. Like, and if you live in a neighborhood, you see that every day, right? Like, there's bunnies everywhere, right? Because we've built all these homes, so we've driven off the natural predators, and so now they just make babies, right? So it's exponential growth, right? So like exponential curve goes like and like shoots up, right? But if we're looking at that curve, it looks like the bunnies just take over the world, right? Like eventually they overpopulate so much that there's 8,000 billion of them. That's not a real number, I'm just saying. But we know that that's not the case, right? At some point, they run out of a food supply or our cars start running over them or whatever, right? And so there's a limiting capacity or carrying capacity for that particular environment, right? So if we're talking about bacteria, maybe we run out of whatever the bacteria needs to grow or blah, 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 right? So what happens is this curve that started off looking exponential at some point curves back off and reaches the carrying capacity, which would be like up here. That would be the L, okay? So it kind of like levels off again. So it starts off exponential and then it levels off. All right. So in this situation, the rate of increase or decrease is directly proportional to both P and L minus P. So the carrying capacity minus P. Okay. And then in other words, this is the formula. Okay. So this is the formula. There's another one down here that we use sometimes as well. This one they just factored out. And we'll talk about that here in just a second. Okay. So this is the new differential equation that takes into account the carrying capacity, okay? So I was going to do a simulation activity. I actually decided not to. There's a thing on College Board that I might have us look at instead. So in example 1, let's just go straight to the examples. I want to keep these notes short so you guys can kind of look at the actual assignment. Suppose that a population of owls develops according to the logistic differential equation. So like I said, they're going to tell you it's a logistic growth situation. And so just kind of keep a lookout for that, especially on this test, right? And then dp over dt here is the differential equation they're giving us, where t is measured in weeks, okay? So the first thing I want us to see is that we can manipulate this equation to look like the equation up above, right? Where we can figure out what the limiting capacity might be. I keep calling it limiting capacity. Limiting number or carrying capacity. I'm like merging the two. Okay. So if I want to rewrite this, I'm just going to do it up here. dp over dt. If I want to factor something out, right? But I want to factor it out where I have like the rate on the outside and then only L minus P left over, right? So essentially I have to think to myself, I only want this to be minus P. So don't think of it in terms of GCF because it's not GCF. What would I factor out to make this just a minus P? Yeah, 0.0002P, right? That would leave me with just minus P, right? All right, and then I'm assuming you guys, one of y'all at least has your calculator. You could probably do it without, but you might second guess yourself because decimals are weird. So then I just want you to divide the 0.02 by what we factored out, the 0.0002. Yeah, it's 100. So now, does everybody see that now it looks a lot more like this? Okay, now comparing it to the formula up above, what does it look like the K is? 0.0002. And what's L, the carrying capacity? 100, right? So what does that mean? What does the 100 mean? Like there's a max number of 100 owls, basically, right? Like it's going to grow, but then at some point there's not enough like mice and rabbits for the owls, and it'll kind of level off, and then there's 100. Okay, there's a huge owl that perches on the back of my fence in my backyard, and it ate one of my neighbor's puppies. So that, yeah, it like swooped down and carried it off, and it was like, my neighbor saw it happen. I shouldn't be laughing, but all of your faces are really, all of your faces are intense. Okay, so yeah, they'll find their prey, but eventually those owls will level off, right? Okay. So it says where T is measured, blah, blah, blah. Okay, so it says if P equals 0, P of 0 equals 5. What is that giving us? The initial condition, right? Then it says, what is the limit as T approaches infinity of P of T, right? So it's asking, as I go all the way to the right of this curve, what's the limit? 100, right? So was that initial condition even necessary? No. So in logistic growth, it's different, right? So at first glance, people might think, oh, I need to separate my variables. I need to use the initial condition, find the P of T equation, then do the limit as x approaches infinity. But in a logistic growth, as long as I can find that carrying capacity, that is the limit as the time approaches infinity. So the answer is just 100 owls. Right?
If they ask that question, would we literally just put 100?
Yep. You don't have to show anything. Yep. Nope. You might show them that you got this into the form where you could find the carrying capacity, but you don't have to explain that. Okay. Yep. And then it says, what is the population when it is growing the fastest? So there's one other thing about the logistic curve. And basically, if we look at this, right, when it's saying when is it growing the fastest, it wants to know when is the tangent line the steepest, right? And what we actually learn is that's halfway between where we start and where we finish. Okay? So it kind of, a typical logistic curve is exponential, and so y equals 0 is the starting point. So this would be about 50 owls. That kind of confuses students sometimes because we have 5 as our initial condition. So some students want to go between 5 and 100. But think in your head, like, if I start at 5, there is a possibility that, like, there was less than that before, right? So we always just consider, like, the exponential curve with the y equals 0 as my horizontal asymptote. And so it's literally just halfway between. So it's where the point of inflection is, if you remember way back to when we talked about those, where it's growing the fastest. Okay, so it's like halfway through, so that would be about 50 owls. Okay, any questions so far?
What work would we show for that?
Nothing. Nope. And that's the thing about logistic growth is you don't necessarily have to show the work. Like that
feels illegal.
It feels illegal, I know. You're like, wait a minute, we just went from unit 6, which like almost like broke us, to then like, oh, just tell me. Yeah. Yeah, just vibe it out. Yeah, just vibe it out. All right, so let's look at the next part here. It says dp dt equals this, right? This is what we just started with. So there is another situation where you can factor out the L. Okay, now L was a carrying capacity, right? So it was a number, right? And so what happened to the L whenever I factored it out? It kind of merged into the K, right? So like LK is some other K. So the L didn't disappear. It's just K was a constant. So we're saying if we factor it out, it kind of like merges with the K and now it's a new K, right? So this is just another form that like if you could get like the 1 first, then it might look like that as well. Okay. All right, this K is one of the solution, is the 1 in the solution equation below. So when they talk about the K, they're talking about the K from this form, not from the previous form. So that's like the thing that you have to be careful of, because when they're looking for the K value, it's actually the K with the L merged into it, not the K from up above. Okay, I think it'll make more sense when we do the actual question. Okay, so let's just look at it. So it's right here. This is exponential population, and B is this. And we're just going to use those two formulas. And I haven't decided yet. I might just give you the formulas on the test. I haven't decided yet, so I'll let you know. Okay. The rate at which the flu spreads through a community is modeled by the logistic differential equation. Now, why would that make sense? For it to be a logistic curve? Yeah, so at first, all y'all start spreading it, and I say all y'all because it's always at the schools first, right? And then at some point, though, everybody kind of gets the flu, right? And then we kind of level off, and then it goes back down at some point, right? But it's not like just all of a sudden a billion people in Salina have the flu, right? There's not a billion people here. So there is a carrying capacity, okay? All right, so blah, 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 differential equation, this, where T is measured in days, okay? So what is our carrying capacity? It's what? 3,000, right? And so that means like the most number of people that could get the flu would be 3,000, and then we kind of like run out of people to get the flu, okay? Up here, let's just do what we had just talked about. Well, not yet. We'll do that in a second. Okay, let's look at A first. If P of 0 equals 50, so what does that mean? The initial condition is 50. Solve for P as a function of T. So what is it asking us to do?
After like 50 days, right? We know.
Just get the equation.
Get the equation, right? So there's a couple of different ways. You could separate your variables, blah, 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 or we can just use this up here, okay? So if I'm going to use this up here, what do I need to find first? What B equals, and how am I going to do that? So B equals, what was L? 3,000. Minus, what was P of 0? Over. Okay, so let's get our B value. I don't have a calculator. I could probably do that in my head, but I don't feel like it. 59. Ooh. So now, let's just use this P of T. What was L? 1 plus, we just got 59, e to the negative kt, and then I need to solve for k. So remember how I said that the k was the k, I probably should have done this on the notebook paper, I don't know, I'm trying to squeeze it all in the notes here. But remember how I said the k that they're talking about in this formula right here is the k from this form, not the other one. So the biggest thing I need to do here is what? What do I need to do because this doesn't look right? Yeah, so what am I factoring out? What would make it look like this? If I factored out 3,000, right? So we're going to rewrite dp over dt, factoring out 3,000. What's 3,000 times 0.001? 3. Good. I was waiting to see if anybody was brave enough to do it in their head. So we've got 3p. What, that looks like a B for sure. 3p times 1 minus p over 3,000. Okay. So I want you guys to see the only thing that really did was what? It changed it from the k being 0.001 to the k being 3. So when I said like this is the k that they're talking about here, if you're going to use this shortcut to come up with the new p of t, you just have to make sure it's the right k, right? Okay, so all we need to do then is rewrite this equation. So this is example number 2, part A. P of t equals 3,000 over 1 plus 59e to the negative 3t. So what they're saying or they're doing is giving us like a shortcut, basically, like an easy way to solve the differential equation because I know it's logistic growth, so it will fit into that particular scenario. So like if it wasn't logistic growth, it might not fit, like I couldn't use this formula. So they do have to say it's a logistic curve or a logistic situation, and then we go from there. Okay, then use your solution in part A to find the size of the population when it's 2 days. So now all I'm going to do is what? Find P of 2. So 3,000 over 1 plus 59e to the negative 6. All right, somebody with a calculator. And this is a population, right? And it's people getting the flu, so it's people. So we are going to round to the nearest person. So same thing, Riker, that we had talked about before. This would be a situation where like they would assume that you know it's people. What'd you get? 2,617. Perfect. So P of 2 is approximately 2,617 people. Easy enough? And then part C says, use your solution in A to find the number of days that have occurred when the flu is spreading the fastest. Okay, so let's think about what we're saying here. What are we saying? Tangent line is the steepest, and we said that that is halfway between 0 and the carrying capacity. So it's really half of the carrying capacity every time, right? So what was our carrying capacity? 3,000, so half of that is? So I just need to set 1,500 equal to my equation. Now, obviously, this would be minus 3t. Sorry, I can't talk and write at the same time. Obviously, this would be on a calculator. Sorry, y'all didn't tell me that was not for me. This would be on a calculator portion of the test, right? So let me ask you this. How would you go about solving this if you were on the calculator part of your test? And I'm asking like you specifically, because there's a few different ways you can go about solving this, and I'm just curious what you guys would do. Esther, can you do me a favor? You see that green thing on my desk? In that front pocket, I should have a calculator. Can y'all like pass it forward? We'll relay race it. Stick, stick, stick. Okay, thank you. All right, what do you think you guys would do? Okay, so you would actually start to solve with algebra and then plug in your answer. Yeah, everybody's like staring at me. I'm like, just tell me what you do. Okay, so let's do that. And then I want to show you an easier, I won't say easier, but maybe a little bit faster way that might eliminate a few errors. Okay, so let's actually solve for the variable and like see what we get and plug it in, and then I'll show you the other way. Okay, so we start by doing what? I would multiply this 1 plus 59e to the negative 3t equals 3,000. And now, if I divide both sides by 1,500, this is just what? 2. And then I subtract 1, so I get 59e to the negative 3t equals what? 2 minus 1. Let's go. 1. It's a Friday. All right. All right. E to the negative 3t equals 1/59th. Switch to logarithmic, right? So negative 3t equals ln of 1/59th. And notice, guys, it's not ln of absolute value of 1/59th, although that's the same thing, right? But we only do the absolute value thing when we're integrating. Some kids started, like, once we do that, they start thinking that, like, when I switch forms, I need the absolute. That's not the case. It's only, like, because I'm integrating, I have to consider that. And then divide, right? So t equals negative 1/3 ln of 1/59th. And, guys, if this was a non-calculator portion of the exam, that would be your answer. Right? That would be our safe stop. How else could they change that? They could pull the negative 1/3 and make this like a negative cube root, which would be in the bottom. So 1 over the cube root of this. Okay, that's a lot. Okay, so let's use our calculator and just see what we get then, decimal wise. So negative, put in a fraction, 1/3, natural log of, put in a fraction, 1/59th. And I really do encourage you guys to use the shortcuts to like put in fractions and stuff to make it look exactly like. If you try to do the divided by thing and then you forget a parentheses in the wrong place, it just kind of messes everything up. All right, is this what you guys got? Now on this one, I'm going to put it's 1.359 days. You can have a decimal of a day, okay? So that would be one that you would probably just put the decimal, okay? Because that would be like, you know, a little less than halfway through the day. If they told you to the like nearest day or whatever, then you would round, okay? Also notice on this one, the truncated and the rounded look exactly the same, okay? Now, I'm going to show you the shortcut. Now, obviously, you need to know how to solve with exponentials and logarithms because this easily could be on the non-calculator part and your answer would just be ugly, okay? And then you would just put days at the end of that and call it a day, right? But I do want to remind you there is a test-taking strategy for solving equations. And it doesn't matter what kind of an equation it is, okay? Anytime you have an equation, you can put the left side into y1 and the right side into y2 and the intersection is the answer. So way up here, I can put 1500 in y1, and then in y2, start with a fraction, 3000 over 1 plus 59e to the negative 3x. And you just have to use x instead of t because we're putting it in our calculator, which is an xy coordinate grid, okay? So if I hit graph right now, I'm not going to be able to see it. One, my window looks crazy, but two, what was in y1? 1500, right? So my y max at least has to be above that or I'm not going to see where it intersects with that, right? So I'm going to do like 2000 there. Am I ever going to have like negative population? No, so I'm going to make my y min 0. And then based on what we actually already know the answer is, right? I know it's going to be between 0 and 3 days, which is what I already happen to have in my calculator for whatever reason. The biggest thing is we're not going backwards, so that there would be no negative days. So you would at least know to put your x min at 0, and then more than likely your x max would be 10 because that's like, you know, the standard viewing window. So I'll just put that because that might be what, if we didn't already know the answer. So then when we hit graph, there's my 1500, and here's where my exponential curve intersects it. How do I find an intersection in the calculator? Second trace 5, enter, 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 and we get the same answer. Okay, so anytime you're on a calculator portion of an exam, you can, and that's any equation. It could be a logarithmic, it could be a trig, anything. You put the left side of the equation, you can do it for quadratics. The left side into y1, the right side into y2, the intersection is the answer. The hardest thing that students find for that is figuring out what the window would be. You kind of have to think, right? I do want to show you that one, it does save a little bit of time. I will say I solve equations pretty quickly, so actually I don't know that it saved me much time. What it will save you from is like any kind of like algebraic mistake that you might accidentally make when you're solving, okay? The other option is if you get 15 minutes per FRQ. So if this was on an FRQ, because this is a part ABC, so it looks like it was an FRQ. If I have like an extra 30 seconds, then I can solve it and then I can check it, right? And then that kind of gives me some like, okay, I think I did it right. Does that make sense? Okay, cool.